deviation for your sampling the standard error of the mean. It's the same as your sample standard deviation. And we know we have a sample in here, so your mean is going to stay exactly the same for your population for this part for our sampling. So our sampling, when we use the central limit theorem, yeah, but it's going to pull it closer to the mean. Everything's going to be real tight in there. Everything's going to be centered more around your mean and a little less on the edges. From this to this, notice that we use the same mean. We use the same standard deviation, but notice that your sample size changed. This is what I was hoping you would get out of the first two. When your sample size changes, you have a larger number to divide by, which gives you a smaller result. If I divide 10 divided by 2, I get 5. If I divide 10 divided by 5, I get a smaller number. So the larger you divide by, the smaller your standard deviation will be for your sampling mean. Now, instead of having a curve that goes like this, your curve has the same exact mean. Notice your mean stay the same. It's just going to get closer and closer to the mean. And you saw with his videos, he did it like 10,000 times or whatever, however many times he did this with sample size 5 and sample size 25. When his sample size got larger, you saw it get more narrower. It was smaller and narrower. As your sample size increases, the mean of the distribution increases. This is false. The mean stays exactly the same. The mean stays the same. It has no effect on your mean. If you don't have these down, I suggest you write them. Okay, another one said a sampling distribution, your sampling distribution, is only normal when the population is normal. And we said there were two ways for them to let us know that it's normal. The first way is to tell us that the population is normal. The second way is for us to have a sample size greater than or equal to 30. So there are two ways that you know your sample size will be normal. Think back to the video. That's why the video was very helpful. He started out with a population that kind of went like all over the place, like he was all over the place with his population. It was not normal at all. He should have really hit 30 instead of 25. As his sample sizes increased, we saw it got more normal. If it's automatically at 30, then yes, we can assume that your sample one will be normal. Or they have to tell us that your population one is normal. When he did 5, it still was not looking the greatest, but as he did a little bit more in his sample, you saw it looking better. These are the two things you're going to have to remember. Either your population is normal or your n is greater than or equal to 30. A lot of you didn't have anything, so I'm sure hoping you write this down. Okay. This was a good one, but you could figure this out so easily. The waiting time in seconds at a traffic light during a red light. They wanted to know, based on your sample, you had n equals 100. So if n is equal to, it told you in your sample, n would be equal to 100. If n is greater than or equal to 30, you have to get a normal curve. That's why you see 3 normal curves. Which one is it going to be? Look at the means. Here's your means. The means are all the same. What has changed?
That's not a less than, so that's not a greater than, so right? That's the standard deviation.
Where?
It's on the distribution. On the side of the picture.
Inside in here?
No.
On the side?
Yeah. It's not a greater than sign. It's an equal.
That's an equal sign.
Okay.
Sorry, that's an equal sign. Your standard deviation started out at your population 11.9. Your standard deviation has to change. Your standard deviation says oh, this mean is different, so we can't take that one. Oh, your mean stays the same, so automatically it can't be this guy. Now, your standard deviation says your new one has to be your standard deviation over the square root of n. This is going to give you your new standard deviation. So it can't be the original one. It's this one because it's divided by square root of 100, which is 10. It just moved your decimal point one place. Do you see that one as almost as a process of elimination? It can't be 2. It can't be b because the mean is different. It can't be a because the standard deviation stayed the same. So which one is it going to have to be? C. We didn't even have to work it out. We could just have eliminated. The mean has to be the same. And the reason the sample is a normal distribution is because n is greater than or equal to 30. N is at 100. Good? All right. Now, we got into starting to use these. Actually, here again, you just have to find the mean and the standard error of the mean. Make sure you get this on your papers if you don't have it now. Make sure you write this down. The breaking distances were normally distributed, so therefore they covered themselves. That's one way to tell us. It doesn't matter how many are in our sample. We have a mean. Pull out your information. Population mean, population standard deviation. You know you have a normal distribution. It's going to look like this. Right? A random sample of 12. This is our sample. We keep pulling out these samples of 12, and we calculate their mean for each one. Then we calculate the mean of all the samples. The mean has to be exactly the same, but the standard deviation will change. The standard deviation says take the standard deviation divided by the square root of 12. So all it does is take this about the mean and push it in a little closer to the mean. There's less variance. Your standard deviation is smaller, so there's less variance. Are you writing this down? Oh, write it down. No, seriously. I want it down. If you didn't have it down, I want it on the papers. Okay? Now, this was a good one because it said, oh, I should have moved it. Oh, I did. I put the information here. It said take this and change the sample sizes. Do one at 24, do one at 36. It's still normally distributed, so that was fine. And I rewrote this information right over here from the population because I needed to move this down.
So, when it tells normally distributed, what is that?
Normally distributed means you can use this. If it's not a normal distribution, you can't use this. Unless your sample size is greater than or equal to 30, then your sampling is automatically normally distributed.
31?
It's good. Even if it's 30, it's good. If it's 29, they have to tell you it's normally distributed.
More?
Yes.
Do you have to round when you get the answer?
Well, technically, your standard deviation, you should probably round to whatever position their standard deviation was.
Alright.
I tend to round to 3 decimal places just because that's what I'm always rounding to, but you could round your standard deviation to theirs, unless it's so close that you have to go one more out, which I don't think it will be. This was your population. This was when our sample size was 12. Here's our sample size of 24. It just affects this piece right there. So if I divide by a larger number, my standard deviation is getting a little bit smaller. See it? If I divide by 36, a little bit larger, my sample size is getting a little bit smaller. So each time, it's just pushing it closer and closer to the mean. It's pushing your mean up. It's got to fit 100% of your curve in there. It's got to take that and squeeze it inside. So whereas it only can go up. It can't go out because you're pushing the sides in. Okay? It's got to go up. Does everybody get this concept?
So, when you get both the answers for each of them, you don't do anything with the answers, right?
They
You
didn't
just
want us
do
to
not.
do anything with it. They just want you to see what happens as your sample size increases. The concept of just this question was to say what's going to change as your sample size changes is your sample standard deviation, your standard error of the mean. That's all. We didn't have to do anything with it. We will in the next one have to do something with it. Okay. The next one is where we start to actually use these things. Okay. The mean salary for an environmental compliance specialist is about $66,000 for all the environmental compliance specialists. That's the population. A random sample of 35 specialists is selected from this population. Do we need to know if the population was normally distributed? No? Why?
Sample size is 35.
Good. The sample size is larger than 30, so I don't care what the population looks like. I know my sampling distribution will represent a normal curve. What is the probability, here's your probability sentence, that the mean salary of the sample is less than 60,000? And it should say mean, like this. The mean salary of the sample is less than 60,000. Instead of pulling one person at random, I am looking at a sample at random from all my sampling means. I still set my same probability statement up. That's my probability statement. I take my mean from my population. I take my population standard deviation, which they gave us, divide it by the square root of n, and I calculate my new standard deviation. That's what you're going to make your graph from. Even though it's narrow, we spread it out so we can use it to see where they're going to fall. But you can see there's less distance between the two values, So we set it up again, we see where 60,000 falls, and we map it out. Use your formula and find your z-score. Everything else works the same. To the left, find your z-score, look up your area to the left of that z-score. Now, if you use your calculator step, you can absolutely use your normal CDF one, but your lower limit, just be careful, your lower limit is still negative 999. Doesn't matter what you call it, negative anything. Put your upper limit as your 60,000. Your mean, you can have it do your standard, you can put this in as your standard deviation. Let your calculator calculate it. Just put that right into the standard deviation spot. Just put in your 12,000 divided by the square root of 35. Then do a paste.
What does that have to do with the other?
Yeah, I was about to ask you.
What is it? When we find a z-score, what do we do?
Well, once you find your z-score associated with this x value of 60,000, you want the area to the left. So you're going to look up your z-score in your chart, and you're going to get the area to the left. Now, shouldn't that be a really small area? Yeah, it should be really small. Because isn't that unusual? Almost really very unusual that it's almost negative 3?
Yeah, but they didn't ask us nothing.
They ask what your probability is. So what is your probability that happens? There's your answer. There's your final answer. I'm just saying if you use your calculator step, your normal CDF works for those of you that like to use that and bypass all the z-score stuff. You can put it in your normal CDF using the same thing, but make sure you change your standard deviation to be divided by the square root of 35.
So
What's the mean?
whenever it talks about probabilities and z-score thing, but just divided by the square root.
Yeah. The only thing is, what am I going to do with that sample size? What extra piece of information did they give us? They didn't pull from a population, they pulled from a sample. I got to be able to put that in somewhere. That changes your standard deviation. Go ahead.
What do you find out?
Okay, what's your normal CDF? Your mean, what's your mean? Your mean doesn't change. 66,000. And then your standard deviation, put this in. It was 12,000 divided by the square root of 35. Just put it, the whole thing right there. You don't even have to calculate it. It's the same as it was before. The only difference is this right here. This is the only difference. Okay? Which means you have a little less area because you're a little closer to the mean. And if you don't understand the calculator, don't use the calculator step. Do this. I still need sketches. Even though this curve in actuality took your one and made it a little narrower, we really can't fit it on both curves and be able to see what we're looking for. So we just spread it out like our normal curve. Can everybody do this? Yes, Mariah.
Can I just, instead of putting like the whole 60,000 minus 66,000 over 12,000, can I just like put 12,000 divided by 235? Or do I have to do the whole entire
12,000 divided by the square root of 35 just gives you your standard deviation on the bottom. If you do that first, where is it? It's here. You could put this number down here instead of doing that.
Yeah, so I can do that.
Yeah, yeah. Bring your standard deviation out. Well, in this case, you probably, theirs is to the dollar. I would just say 2028, 2028. Leave it at 2028. If you put it in your calculator is far more exact than we are. Yeah, if you do this in your calculator, you have to be real careful of your parentheses. So if you do it all at one shot.
Standard deviation doesn't have any decimals, so you round to the whole.
You can round to the whole number. 2028, 2028. Okay. This one said during a certain week, the mean gas price in New England region was $3.796 per gallon. A random sample of 32 gas stations was selected from the population. So, do they have to tell us that your sampling would be normally distributed? No, because why? It's a random sample, but why don't they have to tell us it's normally distributed? Over 30. It's greater than or equal to 30. So notice they don't say it in here. Otherwise, they say it all the time. What is the probability that the mean price for the sample was between, oh, that should be a point, 3.781 and 3.811 that week? Now, the between probability, you set your probability up like you always set your probability up. That has no effect. You still need to find this x value. You still need to find this x value. You need to find your z-score. You still do the same thing. When you find your z-scores, do you subtract your z-scores? No. You subtract your areas. So you're still doing the exact same thing. The only difference is this piece right here. And if, like Mariah said, if you wanted to do this first, take this, and I'd have to go 3 decimal places with that because your original standard deviation goes 3 decimal. Just replace this with 0.008. It makes the problem look not as scary looking, I guess. Find your z-scores. Notice the z-scores are the same. They're symmetric about the mean. Find the areas and subtract your areas. That area, even though, look at this, guys, you're almost from the -2 to the +2. That's covering most of your area right there. That's 95% of your curve from -2 to +2. Makes sense, doesn't it? Can you all do this?
I think we should do some class.
We're going to do some more. Yeah. But, see, here's the thing. If you use your calculator step, the in-between one is the best one to see in the calculator. This is your normal CDF. You have your lower limit. This guy, you have your upper limit. This one, you have your mean. Here, you have your standard deviation divided by radical 32. And paste. And it avoids all of this. This is a little longer to do, but this one's probably easier to understand because your upper limit and your lower limit are actually defined for you. You don't have to think of the -999, +999.
Normal CDF.
Normal CDF. Remember that's your cumulative distribution. Okay? The mean height of women in the United States is 64.2 inches. A random sample of 60 women, so n is greater than or equal to 30. We're okay. What is the probability that the height for this sample, and I should be doing it this way with the mean from the sample means, is greater than 66 inches? Same thing. Lay this out, find your new standard deviation, lay out your curve. Look how close these are now with your new standard deviation. They're so much closer to the mean. Your standard deviation got smaller, so there's less variance. Yes. Look how large my z-score is. I want to know the area to the right of that z-score. Isn't that off our table? So virtually, there is no area to the right. We can't say there is definitely no area. It's minute, minute, minute. Remember, these curves go out forever and ever and ever. They just never touch the axis. They're just like negligible area. So we can say it's approximately 0. What if this said x was less than or equal to 66? What would my answer be? Like about 100%. We would have to say very close to 100%. Because there's no area to the right, that means all the area is to your left. So either you guys are all on target with this, or you're still saying, what the heck? There's no difference, guys, except for your standard deviation. That's it. Just your standard deviation is changing.
It feels
That's
like
it.
it's so much more difficult.
It does, because you know what? It looks worse. It looks worse because the numbers are closer together. That's why we spread it out again. If we were to do 2 1 to 1, that's horrendous. If we had to take your normal one and put the 2.9 and then superimpose the little one on top of it, that's impossible. Really, you'll never see where your standard deviation is at because you have to like redo everything. So that's why I say, just do it once on this side. Okay, we just did 31, but now we're just checking to see what are you, oh, this is a very good one to do. We're doing 31, same thing, mean, standard deviation stays the same. We're taking a sample of 20, and we're comparing the sample of 20 to what if we took just one from the population. This is a great problem because this shows you how much closer I am to a real number by using your samples rather than spreading this all out. So if I choose one from the population, and this is the difference, everybody look up here. Are you more likely to select one woman at random with a height less than 70, this is your population, or are you more likely to select a sample with a mean height, and that should say X bar, less than 70? Do you see the difference right here? One person at random from your whole entire population, and you're checking that person's height. Or versus, give me a sample of 20, let me take that mean and check that mean against our average height. Which one would be a more realistic view? The sample. Think about it. Again, if I took all your heights in here and I randomly selected one person, but if I selected TJ, is his height a representation of the rest of our heights? He's tall. But together, if I averaged him with 5 different people, wouldn't it become more of a better average? And then if I took that average that he's in with this group, this whole group of 5, I could even take this group of 4. If I average this group of 4 in, wouldn't that bring their average closer to the real mean rather than just TJ's height? Do you see the difference? But that's what you're looking at. You have a better chance of being more realistic if you take a group and average them, or versus one person. You never know what that one person's going to do. You're choosing that person at random. Okay? Same thing I told you like with your test grades. If I took the mean average and I said that the mean average was 80 in here, and I took one person, if that one person was my 100 and I'm comparing that, it's better for me to take a sample of 5 that includes that person with the 100. Now I'll get closer to my mean. And that's what it's exactly doing, pushing you closer to your real mean. What's throwing you guys off, and that's why I spent a lot of days up front on this, is the wording. It's your population mean, your population standard deviation, versus the mean of all your sample means. That's your sampling distribution. Okay. Why is it approximately 100? Because this one changed your standard deviation. So now look at what happened to your z-score. Look at the difference in this z-score, because your difference is here. The rest of it's the same. So if I divide by a small number, this is less than 1. Almost half. Versus 2. This is almost 3. That's almost 0.5, let's say. Look at the big difference in dividing by 3, or dividing by 1 even. Isn't it a big difference? So this number, I divide by a smaller number, is going to be a larger number than this guy. On my scale, it's better for me to take a sample and have that be less than 70 versus one person and have that person be less than 70.
So, 100 though?
Well, because that's kind of off our regular chart. Your chart only goes up to 3.49, and then it doesn't calculate anymore because the area is negligible.
The last one wasn't 4.8 or whatever?
Yeah.
Approximately 0?
It's a, well, we were looking to the right of it, remember? This time we're looking to the left of it. 3.49 is where your book ends off your table, but it still goes on and on and on. It'll go here to 20.49 and 800.49, but the area will be so negligible to the right. That area is to the left. Okay? All right. So you're more likely, not that much more, but you still are more likely to choose the mean from your sample means. Number 35 was a good question in the way they asked it. They asked, is this unusual? They're asking, is it unusual? I have a machine that fills milk containers. I have a mean of 64 ounces and a standard deviation of 0.11 ounces. I don't want to lose money and give them more than they're paying for, right? And I don't want to cheat anybody in giving them less than they're paying for. So I want them to stay within a certain range. Obviously, I might not hit 64 ounces every time I fill this bottle, but I want to be within a range to say this is okay. Now, I randomly sampled 40 containers, because just taking one bottle, is that going to be a true representation of my entire population of all these milk bottles? No. So if I sample 40 of them and take their mean and compare their mean to what I'm saying the mean and the standard deviation should be, I'll get a more realistic view. So if technically, if it's more than this, if this is what's happening, if it's more than this, something's very unusual here. If it's within my plus or minus 1, I'm okay. My machine is doing pretty good. But look what happens. We changed our standard deviation because we have a sampling, and that right away tells you, do something with that 40. Don't just leave it hanging there. Do something with it. So I use it to change my sampling standard deviation. I calculate my z-score, and I say, that is unusual. It shouldn't be almost 3. That's very unusual to come out with a mean that high, isn't it? Plus or minus 2 is unusual, 3 is very.
So you can't put that on calculator?
You can. You're going to get your area to the right. Well, why don't you do it with a z-score and get your z-score? That might be even better. Not, use your mean of 0. No.
I tried it, but it came out.
Yeah, Yeah, you would have to use this statement. You would get really small area, wouldn't you? Like from 0, 0 something. Yeah, because it doesn't probably get any more exact than that. Guys,
Next time. Yeah, that. Like,
oh,
what is
this is your standard deviation for your population. This is your standard deviation for your sample. I should put the bar across the top. X bar is the mean from your sample.
I'll probably have to get those.
Okay. Having your